So this is Alvin and Audi's DRSS severity classification with ML models. Starting with some background, diabetic retinopathy is a common eye disease that affects 95 million worldwide. DRSS will be the scale that we use to assess and classify the severity of the disease. As you can imagine, effective treatment, to effectively treat people, early detection and accurate classification is necessary. Looking at the data, optical coherence tomography images, or OCT for short, are what we are using from the prime subset of the OLIVES dataset. The dataset contains 32,000 samples, with about 75% of them used for training and the rest of them used for testing. Severity levels are generated by grouping DRSS scores into three classes as there are three severity levels. So just an overview of the models that we'll be using to classify DRSS severity using the OCT images. The four machine learning models that we will be building range from KNN, random forest, convolutional neural network, or CNN for short, from scratch, and a CNN from transfer learning. The models were evaluated using balance, accuracy, RSC curves, and confusion matrices. Looking at the first model, a KNN algorithm is a simple yet really powerful classification method that assigns a sample to the class based on the neighbors around them. The amount that are present in that population of the vote is a user-specified parameter k. In this experiment, we implemented the KNN algorithm with different values of k to find the best performing model. Looking at the second model, random forest is also based on majority vote. It implements several decision trees, which are also up to the user to configure. We tuned the hyperparameters such as the number of decision trees and tree depth to optimize the model's performance as well.
For the third model, we use a CNN from scratch. Here we have convolution layers that update its own weight. It uses a series of these convolutional layers to extract features from the input data, and followed by a pooling layer to reduce the dimensionality of the features. Then we also use a fully connected layer to classify the input data to different categories to make predictions based on the features. Our fourth model uses CNNs but with transfer learning. A network pre-trained on larger datasets can transfer its learned knowledge to a separate problem set. Here we use inception feed tree as the transfer learning model, and essentially it was pre-trained on ImageNet, a dataset which has around 14 million label images, and they're fine-tuned in the case for the OLIVES dataset to classify the images into the three classes. The overall result, we can see that CNN and transfer learning model outperforms KNN and random forest with an accuracy of greater than 40%. This may be due to the fact that neural networks have better ability to extract features and update its weights while learning. From the resulting confusion matrices, for all the four models, they were biased towards predicting class 1. But overall, there was no trend or consistent trend to be seen. Now for the ROC curves, we could see there are general improvements as we move to more complex model by the increase in the area under the curve. We could see the resulting transfer learning has the highest true positive rate. In conclusion, we noticed that CNNs outperform KNNs and random forests, and that transfer learning specifically performed the best. For future works and improvement, we could do some data augmentation to reduce overfitting, and we could use some feature selections for extracting other aspects of non-CNN approaches. Other than that, we had some struggles with Google Colab, so with running out of memory, so we could use better cloud-based services to run those models. Thank you so much.